So yesterday we were doing something pretty straightforward. Okay. Section 4.4, inverse of a square matrix. At this point, we are doing this assuming that the matrix is invertible. Okay, we haven't really looked at what makes it invertible at any particular stage. So inverse of a square matrix. And again, the idea is that if you have a n by n matrix A, okay, there should be a corresponding n by n matrix A inverse, so that the product A times A inverse and A inverse times A are both equal to the n by n identity matrix. So that is the special matrix with ones along the main diagonal and zeros in all the other positions. In particular, if A is a 2 by 2 matrix, then A12, A21, A22. You can write its inverse as 1 divided by A11, A22 minus A12, A21, which I know some of you might recognize that term as something related to the matrix, but we'll give it a name in a few minutes. Okay. Times A22, A11, negative A12, negative A21. Okay. But this kind of nice setup formula, it works only for a 2 by 2 matrix. It doesn't work for bigger matrices. For n greater than 2, okay, we have to use the Gauss-Jordan method. That is one of the methods, and that's probably the only method we're going to do with matrix inverse. So the idea is to augment the matrix A with the corresponding identity matrix of the same dimension, do the row operations, and convert this A into the corresponding identity matrix. And while you're doing all the same row operations on both sides, okay, this will transform into inverse matrix A inverse. Okay. Of course, if the matrix is not invertible, this will break down at some point. So we only try this with matrices which are guaranteed to be invertible. Okay. So that is the idea. We did one example yesterday, but it's a pretty routine calculation, as I mentioned so many times. Okay. And you'll get a chance to do one of these tomorrow. So just to get a little bit more practice, let's do one more, and this time you will do most of the work. And note that if Ax equal to B is a linear system of equations, then the solution X can be written as A inverse times B. And this assumes that A is a n by n matrix. Okay. That's one of the immediate applications of the inverse of a square matrix. Okay. All right, so before we start doing an example, do you have any questions about anything? So we have a test tomorrow that covers up to and including this section. Okay. So it's a lot of calculations, as I wrote in the last week's announcement, and also I think I listed the problems that you should expect. Any questions? All right, then let's do this example, which should be a pretty good representation of what you should expect tomorrow. Okay. Use A inverse to solve the system. -1, 3, -3, 2, 6, 1, 3, 8, 3. Times x1, x2, x3 equal to -5, -10, -15. So when the question says use A inverse to solve this, it is assuming that the inverse is existing, so which means that there would be a unique solution. So there'll be no free variables or any of that funny business. Okay. So can you try to do this? Just take your time. You might encounter some fractions on the way. Okay, that is purposefully set up that way so that you won't believe that all the matrices are clean. Make sure that you start with the matrix given in the question. Don't change anything before you set up the augmented part. Okay. So don't negate the first row before you put it in. So it should start with what is given and then start manipulating things. If you're doing in a different way, don't change anything. Just keep doing it.
Professor, I think you forgot the negative on the 1.
Yes, I did. Thank you. That's a good catch. Otherwise, I would. This one, right?
Yes.
Thank you. So interestingly, I did the others okay. Is it? That is only mistake I did, right? Okay.
For the last row on that one, I got 0, -1, -6, I think.
Oh, this one?
Yeah.
Yes, it is, because 3 times 3 is not 6, it is 9, right?
Yeah.
That was my mental calculation. That was 3 minus 6, 3 minus 9. Thank you. Okay. Just going to swap these two. Again, you don't have to follow exactly what I'm doing. At the end, it should be the same inverse for all of us. Oh, okay. 1, 3, 3. So I'm going to swap and negate. Okay. Playing dangerous games here. 1, 2, 3. Let's safely get them across. Swap and negate. Right? Now, you could make several choices here. Okay, you could divide the last row by -5 at this point, because you need a 1 here anyway, right? You could do that now or a little later. That's your choice. Okay. So at some point you have to do it. Okay. It's not completely unavoidable, but if you can delay it, maybe that might keep some of the other calculations a little bit cleaner. Okay. So maybe. Yeah, that's your choice. If you don't mind working with fractions, I have no problem. Okay. Oh. So now what I'm going to do is try to create zeros at the other positions. So maybe R1 minus 3R2. One, 0. How did I get that 6 there? -5. Oh, that thing went up there. Okay. All right. R1 minus 3R2, 1, 0, -15. Oh, I'm kind of blanking out on my calculations. -1 minus 3 times -3, 8. 0. That's nice. And 0 minus 3 times -1 is 0 plus 3, right? That was my only thing that I was trying to change. 0, 1, 6, -3, 0, -1. Now I think we have to bite that bullet. Okay, so -1/5 R3, 0, 0, 1, and here comes the fractions on the right hand side. -2/5, -1/5. So they're not too bad, but delay it as much as possible. Yeah, just let me know if I'm making any calculation mistakes. Okay, I hope that one was okay. Now we can do R1 plus 15 R3 to clear up this guy. So it's 1, 0, 0. Let's do this carefully here. So it's going to be 8 plus 15 times -2/5. Okay, that's 8 minus 6, which is 2. We have 0 plus 15 times -1/5, which is -3. And 3 plus 15 times 0, that's 3. 0, 1, 0, 1, 6, -3, 0, -1, 0, 0, 1, -2/5, -1/5, 0. Okay, so far? One more thing to go, right? Take care of the 6 and we should be done. So R2 minus 6 R3 using this one as a pivot. Okay. Will give you 1, 0, 0, 2, -3, 3, 0, 1, 0. All right. So -3 minus 6 times -2/5, which is -3 plus 12/5. That's -3/5. Okay. That's the first element here. Then you have -3 minus 6 times -1/5. Which is -3 plus 6/5. This is -15/5. That's -9/5. Is that right? Any? These should come here, right? Kind of disoriented here. Sorry. Oh, thank you. This is -3/5. This is where I was trying to write it. Not the best start to my day. So this is -3 plus 6/5, which is, that's why you are not keeping, that's why I'm not saying anything. You are just silently observing what is going on. Maybe, he just changed his plan to write everything there for change. Now, test me here. Okay. So this one back here, this is -15/5 plus 6/5. That's -9/5. Is that right?
Professor, I don't think you're supposed to be adding it to -3. I think it's supposed to be added to 0.
R2. Oh, why am I looking there? This one, right? Okay. Get a grip. All right. R2 minus 6 R3 would be 6/5. Sorry about this one. Yeah. I was trying to do this minus this. R2 minus 6 R3. That's easy. -1. Phew. -2/5. -1/5. 0. If you tried it using any other combination of steps, this is what you got at the end. Did you? Anybody online can confirm this or? All right, good. At least one person is confirming, so that's nice. So this is my A inverse. Okay. So our objective was to make use of this inverse matrix to solve our system. Remember that if you pre-multiply our equation with the inverse matrix, it should solve for the variables one after the other, okay, without any additional REF or anything. Now erase that first part of what I wrote here, so you might want to go back and look at what the right-hand side looked like. Okay. So we wanted to solve AX equal to B, and I think B looked like -5, -10, -15. That is easy to remember. Okay. So your X would be A inverse times B. And A inverse is that matrix which you have to copy it carefully. 2, -3, 3, -3/5, 6/5, -1, and -2/5, -1/5. 0 times the vector -5, -10, -15. Please make sure that you write it in this particular order, not the other way. Okay, it's wrong to write it as B times A inverse. You cannot perform that multiplication because they're not compatible. Okay, so please don't write it in this way. It has to be A inverse pre-multiplied to the vector B. All right, so that's going to be 2 times -5, that is -10, plus -3 times -30, that is +30, and plus 3 times -15, that is -45. Remember that matrix multiplication is an inner product of numbers from the row to the column. Okay, so you multiply and add those things. Second row will give you -3/5 times -5, that is +3. Plus 6/5 times -10, which is -12. So again, these are circles belong to circles. Okay, the rectangles belong to rectangles, and the triangles belong to the triangle. -15. Oh, +15. And the last one would be -2/5 times -5, that is +2. Then you have -1/5 times -10, which is again +2, plus 0 times -15, that is 0. Two. It's okay. And that's going to be -55 plus 30, which is -25. 18 minus 12, which is 6 and 4. Yeah. Now I'm doubting everything. Is it okay? Yeah, okay. All right. So that's how you make use of an inverse to solve a 3x3 system. Okay. So you can imagine if you were to do one of maybe a 4x4 or a 5x5 by hand, it will be quite a bit of torture to do this. Well, the people at MATLAB have made things a lot easier. Recently, they just give the matrix, it just outputs the inverse if it is invertible. So computationally, this has become a lot faster over the years. Okay. All right, any questions about that problem other than the calculation mistakes? Any questions? All right. So just as a quick note, okay, the inverse of a diagonal matrix diagonal square matrix, okay, with non-zero diagonal entries will be, what do you think it's going to be? Just make a guess. So if it was just A11 0 0 0 8220 0 0 833 without doing any Gauss-Jordan or any unnecessary complicated calculations, can you tell me what the inverse of this would be? None of those A11 822 833 should be equal to 0. Okay. How do you get a 1 out of that one? You know, don't complicate things, just keep it nice and easy. Yeah, just if this is A, the A inverse would be just the reciprocal of those numbers. Okay. That's why I insist with non-zero diagonal entries, because if one of them is 0, okay, it cannot be done. One of the reasons why a lot of time and money is spent on converting a matrix into its diagonal form so that things are easier to compute and simplify, okay? Because all those zeros are convenient and saves a lot of time computation. Okay, so up to here for test number 4. Okay. Again, that's tomorrow. Any questions about anything related to the test or anything that you are doubtful about in terms of the concepts that you need to study or anything? Any questions? All right, we don't do section 4.5. Okay, so the only remaining section in this chapter would be section 4.6, which is about determinants. And that is the word I was trying to avoid in section 4.4. Okay. Some of you would have seen it in calculus 2 or calculus 3. And it's very difficult to give a proper meaning to it without taking a full linear algebra course. Okay, it's a very useful but very simple looking concept. It's extremely useful in applications. So section 4.6, determinants. I think for most students, this is just a number that means nothing. Okay, but we'll try to see if it has some meaning without getting too technical about things. So given a 2 by 2 matrix, A equal to A11, A12, A21, A22. So let's start with the easiest and the smallest possible thing. Okay. We define the determinant of A as the number given by, so what you do is you multiply these two, okay, A11 times A22. You subtract the product of the other two, minus A21 times A12. Or A12 times A21. Okay. And that's the number we had in the denominator of the 2 by 2 matrix, which we were trying to make sure it's not equal to 0. Okay. So this is what you write as the determinant of A. And usually the way to write it is using just two vertical lines. Okay, so A11, A12, A21, A22 equal to A11, A12 minus A12, A21. So when you see two vertical lines, that means a determinant. If you see brackets, it's a matrix. But what is the significance of this number? Okay, that's a number, but then who cares about this number? So here's a quick meaning of this without getting too technical. You just take your XY plane. Just consider this line going from 0, 0 to the point 1, 0 here, okay, and to the point 0, 1 here. That is the easiest thing you can think about. Okay, a line of length 1 along the x-axis, line of length 1 along the y-axis. Okay. If you complete a square here, of course, the vertices of this point is 1, 1. Okay, and I don't think I should ask you what's the area of the square. All of you know it's 1. Okay. And if you write the vectors of these sides, which means the vertices of this as a determinant, that's going to be the first one, which is 1, 0, the second one, which is 0, 1. So the area of the square is what is given by this 1 minus 0. Okay. So that is the simplest meaning you can give. It gives you the area of a four-sided thing, okay, on the XY plane to start with. And then what you can do is you can just transform the square into a parallelogram which is not exactly located in this position. Okay. So this here, instead of keeping it as a square at the origin with sides 1 and 1, this is the area of a parallelogram, because this rectangle could be kind of squished or sheared to one side by a certain angle. Okay. So it could look at something like this now. So this is the area of a parallelogram whose vertices are given by A11, A21, and A12, A22. So that is the easiest way you can give a meaning to this number, so that it kind of makes sense as to why you're doing this. Okay? Because there's always a geometric meaning to everything you're doing in linear algebra. So the easiest meaning is the area of a two-sided picture. So let's just do a couple of cases here. Okay. So A equal to 3, 2, 1, 0. Okay, so it has got vertices at 3, 2, and 1, 0. So it's still a rectangle. Okay, and the area is given by the determinant of A. You can denote it by the two vertical lines, and that's equal to 3 times 0, which is 0, minus 2, which is negative 2. So the only thing you have to be careful about is when there are positive and negative signs, don't make mistakes. Okay. 2, negative 3, 5, negative 4. This is negative 8 minus negative 15. That is 7. Okay. So just be careful when there are alternating signs, just so that you won't get lost in it. So for a 2 by 2 determinant, things are pretty easy, just a number. Okay. For any bigger square matrix, we have to be careful. So for bigger square matrices, so that means you have n greater than 2. Okay, it could be 3 by 3, 4 by 4, and so on. The determinant of A gives a volume. And that's the easiest you can think about in a three-dimensional context. Okay, from a surface thing on R2, it goes into a volume, a solid in R3. So the determinant of A for a 3 by 3 gives the volume, okay, of the solid created by the 3 vectors. That is the geometric meaning. Okay. How do you compute a 3 by 3? So for that one, you have to get used to a certain process, which is a little bit of a annoying thing to do. Okay. So a couple of definitions to get used to here. One is a minor. So for a square matrix A, the minor of any element little aij, so that is a generic element in the ith row, jth column. Okay, so any element in that square matrix A, the minor is defined as mij just make sure that my notations are okay here. Okay, one second. Yep. Capital Mij equal to the n minus 1 by n minus 1 determinant which is obtained by deleting the row and the column containing n minus 1 by n minus 1 determinant obtained by deleting the row and the column containing the element aij. If you have done determinants, you probably know what I'm talking about. Okay, so if you take any matrix and if you take the element aij, okay, you kind of cross out the row and the column containing that, and you get a smaller determinant of the next smaller size. Okay, if you start with a 3 by 3, get a 2 by 2. Start with a 4 by 4, get a 3 by 3, and so on. Okay, so that is what we call as the minor of Mij. So that's the first definition. The second one, cofactor. Again, for the same square matrix A, the cofactor of any element Aij is given by capital Cij equal to -1 to the power of I plus j. Now, what does this do? Depending on the value of I plus j, this alternates the sign between positive and -1. Okay, so this is equal to +1 if I plus j is even, and it's equal to -1 if I plus j is odd. Once again, if you have done determinants, you probably know this alternating sign pattern, plus minus, plus minus. That pattern is created by this cofactor. Okay. So if you're given a determinant of any arbitrary size, so what you do is you evaluate any n by n determinant we do a cofactor expansion along any row or any column of our choice. Okay. Doesn't matter which one you pick, you'll get the same answer. Okay. Though in calculus 3, we always stick with the first row, but universally any row or column should work. So expansion along any row or any column of your choice. So in each step, you're going to get a minor of the next small order. Okay, so you start with n by n, go to n minus 1 by n minus 1, n minus 2 to n minus 2, and so on and so on and so on till you hit a 2 by 2, which will be a number. So it kind of progressively decreases in its dimension or size. So it depends on how big your given matrix is to decide how many steps you have to do. Okay. So in general, the determinant of A is this is the cryptic notation for it. It's the summation of Cij times Mij times Aij. So what you're doing is taking each element, multiplying it with its minor and the cofactor. The cofactor is just either positive or -1, depending on the position of the element. Okay. This is going to be a next smaller determinant, n minus 1 by n minus 1 determinant. And this is going to be the element of that particular row or column that you're picking. Okay. In action. All right, so that is the mathematical way of writing a determinant, just to replace all these sentences I wrote there. All right, so let's do some examples. Okay, any questions about these definitions or notations? So, example, let's take this determinant A, 1, -4, 5, 2, 3, 7, 4, 1, 3. And I'm going to just do this using two different methods, okay, by expanding along the first row, which is what most of us will do a lot of times, okay. So That is the first one, and also along maybe the second column, just for fun. And let's hope that we'll get the same answer, whichever. And some of you can try even the third row or the third column. Okay, there is nothing special about these two. All right, so first example I'm doing, I'm going to pretend that you have never seen this thing in your life. Okay, so I'm going to go slow with this. Expand it on the first row. The first row elements are A11, A12, and A13. Okay, those are the elements. If you just give some notations to it in the first row, there are A11, A12, and A13. So if you're expanding along the first row, this is going to look like C11, M11 times A11 plus C12, M12 times A12 plus C13, M13 times A13. Okay. I know that looks painful, but we're going to speed it up from the next example. Okay. That is what it means by expanding along the first row means. Take each element, multiply with this minor cofactor. Okay. Element minor cofactor, element minor cofactor. Once again, there is nothing mysterious about this C11, C12, and C13. Cij is just exponent of -1 to the power of I plus j. So C11 is just +1, C12 is -1, and C13 is +1. Because I plus j is 2, 3, and 4. Okay, 1, -1, 1. So we can write this as A11 times M11. Okay, that's because C11 is +1, no change. Then you have this middle one, which is minus A12 times M12 plus A13 times M13. So you can get rid of that cofactor thing as soon as you get started. Okay, just alternate the sign starting from where you are. Okay. In this particular case. What is M11? Well, let me just write the determinant again. I know it's a little time consuming, okay. But just to illustrate what I'm trying to do here. M11 is the minor obtained by deleting the row and the column containing that one. Okay. That is, this part here is your M11. So with some practice, you don't have to draw this over and over and do it. Okay. Kind of, you get used to it in a mental picture, but the first time you have to really write it down and delete the column and the row containing that one. This will give you 3 times 3 is 9 minus 7. Okay. So this is going to be equal to, so A11 is 1 times its minor, which is 3, 7, 1, 3. I know some of you might be cringing because it's too slow. Okay, just bear with me. Okay. So that is your M11. Okay. Then you have minus A12, which is already negative. So actually it becomes a double negative here. Let's just do it one step at a time. Okay. So this negative first and then the negative for the matrix. It's minor. Let me just make use of the same matrix here. 1, -4, 5, 2, 3, -7, 4, 1, 3. Delete the row and the column containing -4. That's going to be 2, 7, 4, 3. And the third one would be similarly delete the row and the column containing 5. So it's going to be plus 5 times the first and the second parts here, 2, 3, 4, 1. And each of these are 2 by 2 determinants. So it's going to be 3 times 3, 9, minus 7, which is 2. This is 6 minus 28, which is negative 22. And this is 2 minus 12, which is negative 10. Okay, so that is how you bring it down to a number. Okay, start with 3 by 3. It will give you 3 2 by 2 minors. Each of them will be a determinant. So now you can combine all these things. So 1 times 2, that's 2. This is a positive 4. Okay, so it's 2 plus 4 times negative 22, which is negative 88, minus 50. And that's a negative 136. In terms of the area, the negative sign just means that the orientation is flipped over. Okay. The area is positive, but it's a parallelogram in the opposite side of the XY plane. That's it. All right, any questions about this? If you understand this, you should be able to evaluate any big determinants. Okay, it's just a question of which row or column you pick. Okay, any questions? Let's do the second column really quick. Keep it there. Again, if you spot any mistakes, let me know. Is that correct? Okay, so that way I can expect the same answer when you do a second column. The problem with the second column is that the way you are going to take the minors are going to be a little bit unusual because it's sitting in and not your typical position. Okay, but that shouldn't be a problem. So this is A12, this is A22, and this is A32. So that is the first row, second column, second row, second column, third row, second column. So expanding along the second column in general would be C12, M12, A12, plus C22, M22, A22, plus C23, M23, A23. Second column, second column, second column. The second index is a column that should remain the same throughout in this case. C12 is -1 because I plus j is 3. C22 is positive and C32 is negative. So if you expand it on the second column, then you start with a negative, then go positive. So it's going to be minus A12, which is -4, times its minor, which we wrote earlier as 2743. Plus C22, that is positive. A22 is plus 3. Times the minor of 3, which is a little difficult to just look and say. So you have to just cross out the middle column and the middle row. Okay, so it's 1543. Minus because of the cofactor A32, which is, I think there was something here. What is it? 1 minus 1 times its minor, which is going to be, delete the row and the column containing this. That's going to be 1527. I know that has become really cluttered at this point, but just have to look around it. Okay. Okay, so that's going to be well, this is what we did earlier. Okay, 6 minus 28 times positive 4. And that was negative 88. This is going to be 3 minus 20, which is negative 17 times 3, which is negative 51. And this is going to be 7 minus 10, which is negative 3. That's a negative of negative 3. Okay. That's going to be negative 139 minus negative 3. And that's good news. So it doesn't matter which row or column you pick, you will get exactly the same answer if you don't mess up any of the positive and negative signs. All right. So that is how you do a 3 by 3. Okay. Just to kind of speed things up for your life. Okay. In future, you can just believe in the following sign pattern for a 3 by 3. Positive here, negative, positive, negative, positive, negative, positive, negative, positive. This is going to be the cofactor sign pattern for a 3 by 3 determinant. Okay. Always, doesn't matter what numbers there are. Okay, this is what you start with. So first row will have this sign pattern. Third column will have a positive, negative, positive, or second row will have a negative, positive, negative. Okay. It's almost like a checkerboard pattern. Okay. So that way you can kind of focus all your attention on the minors of each of these elements. How about 4 by 4? Now, geometrically, we are going into higher dimensions, but just to do your calculations, okay. Evaluate 2, 1, negative 3, 5, 0, 1, 4, 3, 1, 2, negative 1, 4, and 0, 4, 5, 1. Trying to keep the numbers small, but hopefully it won't get bigger when we do this determinant. So it's a 4 by 4, which means that it's going to take more time, okay, because first it has to come down to 3 by 3, then to 2 by 2, then the answer. When you get a 4 by 4 or a 5 by 5 or anything to do by hand, okay, first you should look at all the numbers and see if any particular row or column is convenient to start with. I've created one of them particularly easy compared to the others. What is that one? One of the rows or one of the columns could be easier than the others. We'll get the same answer no matter which one you pick to. Yeah. First column, okay, because of the 2 zeros, this is going to be my favorite column. Okay. So that's going to be my approach. But if you decide to do it along the fourth column, no problem. Okay. You will make use of the zero somewhere, but that will be too many 3 by 3 determinants to handle. So my choice is to expand along the first column. Again, don't get me wrong, that's going to give you 3 by 3s in the next stage. Okay, so there is nothing that you're going to escape in a big way, but at least fewer of them to handle. So let's first fix a sign for this. So this will be a positive, negative, positive, negative, negative, positive, negative, positive, positive, negative. This is the cofactor sign convention. Okay. The signs will alternate with each element. So if you're looking at the first column, that's going to be a positive, negative, positive, negative. So it's going to be 2 times the minor of 2, which is going to be a 3 by 3 determinant obtained by deleting the column and the row containing 2 That's 1, 4, 3, 2, negative 1, 4, 4, 5, 1. That is the first one. The second one is a 0. We are lucky because that's a minus 0 times whatever. Okay. So let's just as a placeholder, just keep it there so that you don't mess up the cofactor signs. The next one will be a plus 1 times its minor. Okay. So you have to delete the row and the column containing 1. So it'll be 1, negative 3, 5. 1, 4, 3. These signs up here, these are for the cofactor, don't give it to the numbers. Okay. The numbers are still 1, 4, 3. And 4, 5, 1. And the last one is again plus 0 times. So we don't care about the second and the fourth numbers. Minus. Okay, that is the convenience of choosing the first column. But as I said, if you pick the second column, okay, you will end up with 4 of the 3 by 3 minors, but 2 of them will be 0. Okay, that's a good thing. All right, now can you compute those two 3 by 3s and see how that goes? So it's a good practice. You have to reset your sign convention each time you come to the next minor. Okay, so 3 by 3 is back to this. So don't restore the signs from the previous one. This will be back to plus minus plus here. You don't have to put it for all the terms, just for the row or the column that you're picking, just focus on that one. Unless there is anything particularly advantageous about anything, I would typically stick to the first row. Okay, that is the safest place to be in. So it's just positive, negative, positive. Because there is no row or column which is anything attractive. Kind of speeding up a little bit now. Okay, now that you have seen a couple of examples, plus 3. Speeding up also means chances for mistakes. So one. Don't forget there is a 2 multiplying out there. Okay, CC2 is that. So this is 98 minus 20. Is that right? Can somebody confirm if that answer is correct or not? Online or offline?
Yeah, that's
Okay,
correct.
good. Thank you. One. Again, first row. Okay. Minus -3. One, 3, 4, 1. It's 4 minus 15, which is -11. -11 times 3, which is -33. All these are -11. Okay. I didn't plan that. Okay. 55. Oh. I should play a lottery today, maybe. So it's 25 minus 16. All right. So again, please don't forget the 2 there. Okay. It's 2 times 77 plus 1 times this, which is minus 99. Okay. So that is 154 minus 99, which is 55. All right. Okay, so that is how you do a 4x4, okay, without going crazy. Okay. There's a slightly kind of a trick question. Okay, evaluate the following 5x5 determinant. Zero, 1, 4. Now, if my evil intentions are correct, what is the value of this determinant? How do you know that it's 55? Mm-hmm. Oh, really? Is that it? Oh, that's magic, right? How did that come here? Okay, so use the fifth column. Okay, I don't care what those numbers are. That's why I wrote some really big numbers here. Okay. Expanding the first column, just make sure that your sign conventions are okay. Positive, negative, positive, negative. That's positive, negative, positive, negative, positive. Okay, good. So that's 1 times this 4 by 4 matrix, which is equal to 1 times 55, which is 55. Of course, you could expand along the fifth row if you want. You'll get the same answer. That's because I used the same 4 by 4 from the previous example there. But typically, if you just start a 4 by 4 or 5 by 5 randomly, it's going to be a nightmare. Okay. All right. Any questions on evaluating determinants using cofactor expansion? All right, now let me ask you to observe a few things and tell me what you think is happening. What is the value of this determinant? It's not a trick question. What is it? It's 0. Okay. Is there any property that you can kind of deduce out of this example? Geometrically, that means that you're looking at the same point. There is no area here. Okay. 1 is a point, and then 2 is just a multiple of 1. Okay. So there is no rectangular square constructed out of these vertices. What kind of a property can you say about determinants based on this example? Same vectors. Okay. So in a simpler way of saying this, no inverse. All right. So if a determinant has the same rows or same columns anywhere, the value of the determinant is equal to what? Zero. Okay. So for any n by n determinant, if any 2 rows or any 2 columns are the same, sometimes you have to look carefully because it might be hiding in somewhere. If any 2 rows or any 2 columns are the same, then the value of the determinant is equal to 0. Okay. Doesn't matter what else is there. Okay. It could be full of all kinds of fancy numbers, but if any 2 rows or any 2 columns are the same, that means, as somebody wrote, they're the same vectors. Okay, it's not creating anything geometrically relevant, or as somebody else said, there is no inverse. Okay, those are the things that we could write later, but that's the most important part here. Determinant is 0. Also, if any row or any column is full of zeros, what do you think the value of the determinant is? It's a 0 because you can expand along that column or row. Okay, the determinant is equal to 0. All this will have some meaning later. Okay, so please pay attention to these concepts because the calculation is all nice and fun. Okay, this determinant equal to 0 is going to have a very big impact on our life. Okay, in a small way. Number 3. What happens if you interchange the 2 rows of the determinant? So for example, if I take the determinant, say, don't take this one, okay, that is too silly. 2, 3, 4, 5, and 4, 5, 2, 3. Are they the same or are they different? or are they different in a very small way? Yeah. Negative of the other. Okay, so this is -2, this is 2. Okay. So swap 2 rows of a determinant, then that changes the sign of the determinant. Okay, so it's not like swapping the 2 rows of a matrix. Okay, there you could do that for free. You don't have to worry about changing anything else. Okay. If you swap the 2 rows of a determinant, that comes with a price of changing the sign of the value. Okay. Property 4. Okay, this is pretty useful if you don't want to do cofactor expansion. Okay. The determinant of triangular or diagonal matrix what do you think it will be? I'm going to show you an alternate way of computing determinants. Okay. If you have a triangular or a diagonal matrix, what do you think the value of the determinant would be? Just take a 2 by 2. Okay. If you cannot see clearly what's going on, so you can take A11, 0, 0, 822. Okay. Or you could even have, say, some number here. What did you say? Yep, the product of the diagonal elements. Okay, so the determinant of a triangular or a diagonal matrix is always equal to the product of the entries along the main diagonal. Which means that it is worth the diagonal elements, not the off diagonal elements. Okay. It is worth thinking about the possibility of reducing a determinant into a diagonal or a triangular form and use that property to compute things instead of doing the cofactor expansion. Okay. Just as an alternate way of doing this, if you want to. So we can row reduce a determinant into a triangular form. Okay. It could be upper triangular or lower triangular, doesn't matter. Okay, as long as there are zeros either below or above the main diagonal into a triangular form. And use property 4. Comes with a couple of caveats. Okay, you should be careful when you're doing this. So if you're not a fan of doing this particular process, don't do it. Okay? But if you want to do it, you're certainly welcome to try this. One of the things that you should be careful about is the one I wrote up there. If you swap 2 rows, you have to be very careful. Okay. You have to keep track of every time you're swapping something, you have to put a negative outside. Okay. So be careful. About sign change with row swapping. If you swap the rows twice, you are back to square one. That's okay. If you swap it once, it's a negative. Okay. But you can always do a row plus or minus a scalar times another row. Okay, that is okay. That is the only thing you can safely do there. Okay, you can take one row, add or subtract multiple of another row. That's something you have done so far. Okay. Do not do the following. Do not just multiply or divide a row or a column by a number. You could do this one. You could multiply or divide and then add it to another row. That is okay, but don't just multiply or divide a number to another row. Okay, and this is why this is 2, 3, 4, 5. That is 10 minus 12, which is -2. Okay. Just for fun, let's multiply the first row by 2, and let's write 4, 6, 4, 5. That is 2R1. What is the value of the determinant now? That is 20 minus 24, which is -4. Okay. That is not the same. Okay, so you should not do just multiplying or dividing unless you are doing a proper scaling at some point. Okay, don't do that part. You could do a row or column plus or minus another row. That's okay. You can swap rows. Just keep track of the sign change. So I'll show you one example just for the sake of convincing that this works. Okay, but it's your choice whether you want to adopt this for any of your problems. But please remember this property. Okay, that might be handy on test number 5. So I've got a special determinant here, which I know will work. All right, so evaluate the following by doing row operations. Two, 4, 2, 1, 4, 3, 0, -1, -6, 0, 2, 0, and 0, 1, 1, 2. All right. You could do it by any of the other methods. You could just expand along row 3 or yeah, I think row 3 is the easiest. But let's just try this by row operations. All right, so I'm going to do R2 minus 2R1. Okay, we're not getting an REF here. We're not really trying to get ones here. Okay, so there is a 2 there, there is a 4 there. So let's do R2 minus 2R1 and R3 plus 3R1. That is what is allowed. Okay. I wrote somewhere here that you could do row plus or minus a scalar times another row. That is fine. So this is 2, 4, 2, 1. Just going to copy this from my notes just so that I don't have to struggle with my calculations. Okay. 0, -5, -4, -3, 0, 12, 8, 3, and 0, 1, 1, 2. So the first and the last rows are the same. The second and the third rows have changed. Okay. Now I look at row 2. I see this 1 here, 0 there. Okay, so I'm going to swap row 2 and row 4 with a small warning in my head that I should keep track of a negative sign. Okay, so swap row 2, row 4. Okay, so just keep track of this. Okay, -1 multiplied once to the value of the determinant. So that's 2, 4, 2, 1, 0, 1, 1, 2, 0, 12, 8, 3, and 0, -5, -4, -3. Okay, so this -1 ones means I'm swapping, so there is that small change. Yeah. I did this so that I could do R3 plus 5, so R4 plus 5, R2. That's 2, 4, 2, 1, 0, 1, 1, 2, 0, 12, 8, 3, and 0, 0, 1, 7. Okay. Was also planning to do R3 minus 12 R2. So it's 0, 0, negative 4, negative 21. So I do R4 plus 5 R2 and R3 plus 12 R2. All right, I think it might be a good idea to bring this 1 in this position. Okay, so I'm going to do another swap, R3 swap R4. The good news is that we have done -1 twice. Okay. So we are back to the original sign. So in this case, we escape the wrath of the row swapping. Okay. All right. R3 swap R4 will give you 2, 4, 2, 1, 0, 1, 1, 2, 0, 0, 1, 7, and 0, 0, negative 4, negative 21. We are trying to get a triangular matrix. That's why I'm doing all the swapping. Okay, we need a triangle of zeros below the main diagonal. And now you can do R4 plus 4 R3. It's 2, 4, 2, 1. 0, 1, 1, 2, 0, 0, 1, 7, and 0, 0, 0, 7. Okay, that is a upper triangular matrix because we got zeros below the main diagonal. This is the main diagonal here. So there are zeros below it, and that's the property that I wrote earlier. If this is what you get, the value of the determinant would be 2 times 1 times 1 times 7, which is 14. So it's a question of, is that really time saving, or is it easier to avoid mistakes using this compared to the cofactor method? It's a personal choice whether you want to do this. But if you are a computational person with a much bigger matrix, and if you're writing a code for this, okay, I think this is more efficient because the REF process is much quicker than the cofactor expansion. Yeah, so the -1 once means you're changing the sign, -1 twice means you're back to the same sign. Okay. All right, so to finish off this lecture, let me just write down probably the most important theorem of your linear algebra semester. Okay. Please write this carefully. This is super important for test number 5 and also test number 6 in some form. I'm going to make a clear space here. So, and this is part of what one of you wrote earlier in terms of inverse. Okay, so the invertible matrix theorem. This will kind of dominate your test number 5 in a very kind of short and quick way if you know what you're doing. So. All right, the invertible matrix theorem. Let's assume that A is a n by n matrix. It doesn't have to be for any particular value of n, could be any square matrix. And let's assume that the determinant of A is not equal to 0. Okay, when I say not equal to 0, it could be anything, 1, -5, okay, pi, whatever it is. So that is an example of a determinant that is not equal to 0. The following statements are all true or all false. Okay. So the way to write this is the following statements are equivalent. The word equivalent in math means that if one of them is true, everything else is true. Okay. Statement 1, the matrix A is invertible, which means that A inverse exists. So that's a good thing to check before you start wasting your time with a 5 by 5 matrix, for example. Find the determinant, make sure it's not equal to 0. If A is invertible, the system AX equal to B has a unique solution. And that solution is given by X equal to A inverse times B. Okay, that's what we did earlier in section 4.4. Okay. The only condition is that the inverse should exist. And what is the checkpoint? The checkpoint is that the determinant should not be equal to 0. Okay. If this value is something that is non-zero, you are guaranteed a unique solution. It doesn't tell you what the solution is, though. Okay, that you have to find yourself. Statement 3, the homogeneous system AX equal to 0 has a unique solution. Can you tell me what that is? What is that only solution for AX equal to 0 in this case? If I ask you something like that, there should be some unique thing that is there, you know. What is the only solution to this if A is invertible? I'm expecting a number like 0. Okay, good. X equal to 0. We wrote this yesterday as well. X equal to 0 is always a solution. If it is unique, it has to be the only solution. Okay, please get used to that statement. Okay. Statement 4, the rank of A is equal to n, which means that there is no row which is full of zeros. Okay, that cannot happen because the matrix is invertible and the determinant of A is not equal to 0. So this means the matrix has a full rank. Five, the RREF of the matrix A what do you think we will get if you row reduce the matrix A into RREF if it is invertible? What do you get using the Gauss-Jordan method when you do the identity matrix, right? So it's the n by n identity matrix, always. Okay. You cannot get this if the determinant is equal to 0. So the not equal to 0 part there is a checkpoint there. Okay. And I think the sixth one is probably a side result of number 2. The system AX equal to B is consistent, okay, which I could have combined with this one here. Okay. Because it has a unique solution, so it is consistent. All right, so write those statements carefully. You don't need it for tomorrow's test, but you will need it a lot for test number 5. Okay, we will write this again on Monday, just so that you get used to these things. Okay, try to think about what happens if the determinant is equal to 0 and all these cases. Okay. Everything is going to flip over. So that is where the theorem works both ways. Number 4, oh, that's because the rank of A is n, means there is no row full of zeros. Remember that if there was a row full of zeros, then the determinant would be equal to 0. Okay. But we started with the condition that the determinant is not equal to 0. So you cannot have rank less than n. All right, that's it for today. We will, what day is today? I kind of lose track of days. Is it Thursday today or Wednesday? Okay, all right. So to say, good luck with your test or something. All right, test is tomorrow. We'll start chapter 5 tomorrow slowly. Okay, but study for the test. I have office hours at 12:10 today. And, yeah. This is not for the test, okay, so don't worry about this one. Thank you. And sorry if I was a little bit off at the beginning of today's lecture.
Thank you.
Thank you.
Thank you. Let me stop recording.